Okay, close them up, scoot forward for a second while we go through this, and then you'll have a chance to work. This won't take real long, but I want to go through an example. This is kind of interesting. We were in cold weather. We'll do a little investigation here to see why it is that you have to insulate your pipes or take measures in cold weather to make sure that your pipes don't freeze. This will tell us why. Let's take this example. So this is true about water. Water's volume increases by 9.05% when it freezes. Okay? The bulk modulus of water and ice, ice is a little bit, we'll just use water. It was close enough, is 2.2 times 10 to the 9th from our chart. Okay? Newtons per square meter. Water is contained in a cylindrical container with a height of 54.5 centimeters and a radius of 13.1 centimeters. Okay? When the water expands, we want to know what kind of force is going to be exerted on each of the end caps of this pipe. Okay, so this comes down to, this is exactly analogous to both of the other kinds of deformation situations we've looked at. We looked at stretching and compression, right? Tension and compression, and the amount that an object is stretched or compressed has to do with Young's modulus. We looked at, oh, where's my meter stick? Well, anyway, we looked at, I don't have it here. Oh, there it is. We looked at shear forces, right, where we've got a lever and we're pushing on it and bending it, right? And so the amount that an object bends is same kind of deal. It's proportional to the shear modulus, right? And so for water, for any kind of water or any other kind of solid or fluid, when it expands or contracts, it exerts a force, right? So in this case, the water is expanding, and so as the water expands, it's going to exert a force on any container that's containing it as it expands, based on the strength of the bulk modulus. Yes, sir?
Isn't water like the only fluid, kind of?
That expands?
Well, that's like naturally present, like normally. Like what, is there any like chemical fluid that we see, or that we would have seen before like we synthetically generated it?
That does what? That does this?
Does anything like it, is there really like any fluid like that at all?
I think there is a fluid. I think there are fluids like that, but I couldn't tell you any. It's very rare. This is really significant, actually. We'll take a little detour for just a second here. This is kind of interesting. So the fact that water's volume increases when it freezes, what does that do to its density? Decreases, right? Give me proof that the density of ice is less than the density of water.
It floats.
Yeah, ice cubes float in the glass, right? Okay, most objects, when they become solid, their density would increase, and they would sink.
Would orange juice do that?
Orange juice is water, so orange juice would. I mean, it's almost all water, so it would act very much like water. Same thing. So now think about this. If water didn't do that, just that one little fact about water is responsible for large-scale life on Earth. Okay, because if water didn't do that, if ice sank when it froze, what do you think that would cause? Think about places where it's really cold. What would that cause to happen? Well, so the way it is right now, like if we take a pond in the winter, what happens in the pond as the temperature goes down?
It freezes.
Freezes where?
On the top.
On the top. Okay, that's important. It freezes on the top. So if it freezes on the top, why is that significant and important?
You can ice skate.
Say it again.
Life can continue.
Life can continue below. So you can ice skate, exactly. Otherwise, we couldn't ice skate. Why would life want to exist if we couldn't ice skate?
Or the polar bears.
Exactly. But now, so theoretically, that by itself doesn't explain, because what could happen then, here's the alternate scenario. If water didn't have this property, water would freeze on the bottom of a lake, and then the fish would just swim around on top, right?
It would freeze on top.
Okay, but if water froze and then, so if water sank as it froze, right? The ice would collect on the bottom.
And then it gets stuck on the ice.
No, 'cause it's not gonna fall as one big sheet. What's gonna happen is,
Oh.
it would just
Freezing bottom.
freeze on the bottom, right? So the fish would just end up on the top then, right? Okay, what's the problem with that scenario though? It wouldn't work that way. Well, if that happened,
It would freeze
very,
over
very
the
quickly, what
entire-
would happen, every place where where the temperature was below freezing for any amount of time, the lakes
All
and
the-
ponds would freeze solid, but they don't. But why would they freeze solid in that case?
Because they just build
Because
up.
there's always-
What's causing the water to freeze? The
Contact
ground or
with
the air?
Contact with the air.
The air. The ground, in fact, is never gonna be, the ground is gonna maintain a fairly steady temperature, right? The air is what's causing the water to freeze, and so if the ice collected on the bottom, then you'd always have water exposed to the cold air, and so the water would just freeze solid, right? In fact, during ice ages, that would have happened to the oceans. And so there would not have been any large-scale life that had survived the ice
The
ages.
whole ocean would freeze in the ice age.
Yeah,
Wow.
yeah. Because it would freeze from the bottom up, right? As it freezes from the bottom up, that does bad things in a couple ways. It insulates the water from the warmer seafloor, which would normally warm the ocean, right? But it's gonna insulate it from that. So it's gonna be like taking your, hold on, what's an analogy? Like if you were to,
Freeze in the ocean.
well, okay, so let's say, here's a small scale analogy. Let's say you had a burner on very, very, very low, right? Very, very low. And you put a big metal pot of water in there in a really cold room, right? If the water might freeze on the top, but that little bit of heat energy coming in from the bottom is gonna prevent the rest of the water from freezing, right? What if, though, we did this in like a really effective, good quality cooler that's well insulated? Then the heat would never get up from the bottom to the water and it would freeze more easily, right? So putting that ice on the bottom of the ocean is a double whammy. It's going to insulate the earth from the warming of the water from the warming effect of the seafloor, plus it exposes the upper layers of the water to the cold air, and so pretty quickly, the models show, pretty quickly it would freeze the ocean solid. Ice ages last a long time. Ice ages don't last for a year or two. Ice ages tend to last for long periods, thousands of years, right? And so over thousands of years, it's pretty clear that, yeah, the ocean would end up freezing. And if the ocean froze solid, large-scale life can't survive being frozen and thawed. I mean, some small animals can, but mammals can't, right? And so we wouldn't have large-scale life. So that really simple, isn't that weird? That simple little property of water is one of the many numbers that are dialed in just right so we can have life in our universe. Okay, but I digress. So let's look at this equation then. Let's learn a little more about this. So this is just another example of stress being proportional to strain. What's stress? Do you remember? Well, but I mean, what's stress is the ratio of what to what?
Force to area.
Force to area. It's like pressure. Okay, so the way when we talk about stress and strain, stress would be the units of pressure. So we get force divided by area is proportional to strain, and strain is always going to be a unitless quantity that's going to refer to the change in a quantity divided by the original amount of the quantity. Like, for example, with lengths, when we did Young's modulus, we said force divided by cross-sectional area equaled Young's modulus times delta L over L naught, right? So we're talking about changes in length, compression or stretching. Then the force that's required to stretch something would be divided by the cross-sectional area, like of this stick, would just equal Young's modulus for this material times the amount that we're stretching it compared to the original length, right? I mean, you've done a bunch of stuff with that. For shear modulus, it looked almost exactly the same, only that became an S for the shear modulus, right, for shearing forces. And this became a delta X, because now this is the length, but that's delta X is how far we're bending, right? Well, for water, what's it gonna be? Or for volume?
V and delta.
So that's gonna be a delta V over V naught. And what's the constant of proportionality gonna be? Well, what relates the stress to the strain when we're talking
Bulk
about?
modulus.
The bulk modulus, yeah. So our equation just looks like F over A equals bulk modulus times delta V over initial volume, right? Okay, now the area is a little different here though. This is the part I want to really talk to you guys. I want to make sure you understand this. When we talk about areas for Young's modulus, for stretching or compressing, or shear modulus stuff, right? We're always talking about the cross-sectional area of the object that was either being compressed or stretched or bent, right? Cross-sectional area only. That's not what this is about, right? This is a different area. If I take a cube, let's say, I'm gonna forget X. It's by X. Oh no, X. There we go. Okay, so if I have a cube like that, and the cube is going to expand, what area do you suppose I'm talking about?
Surface area.
The surface area. Yeah, right, the surface area. So if I had, for example, a block of water, and the block of water is going to expand into a block of ice as it freezes, as it expands, it's going to be exerting a force outward. It's going to be exerting a force outward through against anything that's pressing against it, right? The force is going to be exerted via the entire surface area of this thing. Yes, sir.
Of the inside of it.
Well, okay, no. We got to be careful about that. So if we're talking about, visualize a block of water, right? The block of water that's being held in place, I don't know how, it's being held in place with some kind of fancy electrostatic fields or something, some Star Trek stuff. As it freezes and it expands very slightly, anything that we're pushing against it would feel a force, right? Where's the force coming from? Well, it's coming from the fact that there is going to be a force exerted by the walls of that block of water, right?
Yes.
See what I'm saying? So there's, does that make sense?
So if you had a cube filled up with water, and you froze it from the inside,
Yeah.
they would press upon the inside surface area of the cube.
Right. Okay, maybe an easier way to think about it would be, what if you wanted to compress water? What if you wanted to compress, water is what we call an incompressible fluid. Not true. It is compressible. It's just very hard to compress. If you want to compress that cube of water into something slightly smaller, well, how much force is going to be required? That's the equation that tells you, right? How much do you want to change the volume? If you want to compress it, by changing the volume, you're going to be making each of the sides a little smaller, right? To change the volume, you're going to have to exert huge amounts of force against all of the surface areas. Yeah.
Is the surface area of the inside of the cube the same as the outside?
Yes, it is. Same thing. Yeah. Okay, but this is a little bit inconvenient to do sometimes. Think about this. The force is going to be changing in tandem with the area, right? Instead, here's a better way to think about this. I don't think the book mentions this, but this is really a good way to do it. What is force per unit area?
Pressure.
Pressure. Yeah, that's just pressure. Right? And so we could just think of this in terms of what's the pressure required to compress water, right? And that's an easier way to think about it. If you go deep into the ocean, very, very deep into the ocean, the density of water is higher. How come?
Ton of pressure.
It's compressed, yeah. Because there's a lot of pressure, right, that's acting on all of the water, the weight of the water, and then a little bit of weight from the air also, but the water just dominates. The weight of the column of water above your depth is going to provide this pressure that's going to cause the volume to change, right? It's going to get squeezed. Okay? So let's go back to our problem then. This is the simple equation we're going to use. How are we going to figure this out? Okay, so let me rewrite this, give ourselves a little room. So here's the equation we're using. Stress, so force per unit area, which is just pressure, equals bulk modulus times delta V over V naught. Okay? So how do we interpret this statement up here? The water's volume increases by 9.05% when it freezes. What is that?
Volume.
Well,
That would
if
be
it,
delta V over V.
that is delta V over V, isn't it? You see that? Right? Let's take an example. Let's use numbers. What if I told you that the volume, the change in volume was 1 cubic meter, and we started off with 10 cubic meters of volume?
That'd be 10%.
Well, the units cancel, I get 1/10, which is the same as 10%, right? So isn't that a 10% increase? Which makes sense. 1 is what percent of 10? 10, right? So we changed the volume. The volume increased by 10% of the original volume, right? Okay, so this fits the problem pretty well, doesn't it? So what's the value of delta V over V then?
0.09.
Okay, good. We have to write it as a decimal, don't we? So 9.05% is just 0.0905.
So with problems with these, we don't actually have to find volumes.
So
That gives
no.
us a percentage.
No, you don't. I gave you some extraneous information here. You don't really need it. You don't really need the volume of the cylinder, do you? Right? All you need to know is how much is the volume changing, right? So this is going to be, so this whole term then just ends up becoming 0.0905 V equals pressure.
Oh my God.
How about that, right? And so what is the bulk modulus for water is 2.2 times 10 to the 9th newtons per meter squared. And so what does that give us? Multiply that by 0.0905. And we get the pressure, right? If we just plug this number in, because this is the bulk modulus for water, right there, what do we get for our pressure?
So we don't even use the height.
No, you don't even have to.
I got 199.1 million.
199.
1,100,000.
Okay, so what is it in scientific? So about, I'll just do that. 190, so it's roughly
2.0 times 10 to the 8.
times 10 to the 8th, right? So it's roughly $200 million, 2 times 10 to the 8th newtons per square meter. A newton per square meter, as you might expect, pressure is kind of a big ticket item in physics. We talk a lot about pressure, so pressure must have some standard units. The standard units are called pascals, and what do you think 1 pascal is equal to?
1 newton per meter.
1 newton per square meter. Right. So this is equal to 2 times 10 to the 8th pascals, capital P, small a. Okay? So let's do a little calculation here. So that's the pressure, right? Let's just stop there. We haven't quite answered the question yet. But let's just do a little calculation. About the huskiest copper tubing you can get, I believe, this is close enough, has a burst pressure of about 3,800 psi. And that's about the huskiest copper tubing, which is what most water pipes are made of, right? So let's do a little calculation here. 3,800 psi is how many pascals? Okay, so somebody just look up the conversion. I don't want to deal with the conversion. So 3,800 pounds per square inch times, what's our changer going to be? How many psi per pascal? Actually, it's going to be, yeah.
I don't have any calculation.
You can look
Yeah,
too.
that's what's like at my house right now.
Yeah, that's up.
It's giving me 2.6.
How-
1 psi is equal to 6,894
Pascal.
pascals.
Like 262.
Or 0.76.
But it's gotta be,
It says 1.
okay, yeah, 1 PSI is gonna be lots of pascals. How many pascals?
6,894.76.
So about
That's not
95.
what Google says.
No,
That's-
he's saying 1 Pascal. That's you Google.
What is,
No,
what
one-
is yours,
1 psi.
is yours saying 1 Pascal equals,
So I have like the 5 minutes.
okay, what is it?
2.62 e to the 7.
2, say it again, 2 point,
6.
Mom, you have it.
okay, take,
2.62 e
okay,
That's not anything.
to the 7.
times 10 to the 7th.
Yeah.
Okay, so, and that's pascals. What's the problem there?
It's off by about.
It's not
off by a
enough,
lot.
right? Look what happens.
Are you
The force exerted by the water is, you know, it's almost 10 times bigger than the bursting pressure of the pipe. And that's the husky stuff. I mean, most, like the water pipes in your house are probably under 2,000 PSI. And so it's not a surprise that when water freezes, it causes problems, right? It bursts pipes. And it'll do the same thing for cast iron pipes. I mean, it'll even actually, it'll rupture an engine block or something, even though that's cast iron. I mean, you get such large pressures in there. And it doesn't need to change very much. The thing is, it doesn't even have to change by 9.05%. I mean, it's probably going to be constrained at some point, but if it's, that's how much it wants to increase. But it's going to exert even more pressure to change by a small amount, if that makes sense, right? It's going to push, the more you compress something,
The harder
I explained that very terribly. If you think about, this all goes back to, I can make this work, this all goes back to Hooke's Law, right? Hooke's Law just said that if we take a spring and we stretch the spring, remember we did an experiment up here, if I double the stretch of the spring, what happens to the restoring force? Increases by a factor of 2, as long as we're within the elastic limits, right? So the same thing is true with water turning to ice. If the water expands twice as far, it's exerted, how do I say this, it's exerted,
Twice as less per increment
right,
than it did originally.
right. Yeah, how do I explain this? That's not gonna work. The force required to compress something. Okay, I think of it this way. Yeah, here's a good way to do it. So, right, so I don't wanna do this, man. This is hard to explain in terms of that model. It's not gonna work. Think about what's happening at a molecular level when this is happening, right? What's happening is the restoring force is coming from the fact that you're pushing these molecules against each other, and the little forces, the intermolecular forces, do a little chemistry here, intermolecular forces, the electromagnetic forces that are causing the molecules to repel, those are being brought into play, right? When I push these molecules out of their comfort zone, so to speak, right? I push them closer together, the electromagnetic forces are going to cause them to be repelled. And so the closer I put those particles together, the stronger they're repelled, right?
Yes.
Does that make sense?
So just like magnets.
So less volume, right, exactly.
So
And
it's
so,
so it's just like the magnets when you put the same ends together.
right, exactly. And so objects are, the water's going to want to expand through a large volume, but even, it doesn't even have to expand through a large volume to burst the pipes, right? It's just that it wants to expand through a large volume. Does that make sense? I mean, so it can burst the pipes even by just expanding ever so slightly. The pipes are solid, right? They're going to crack. Plus, when copper gets cold, or any metal gets cold, it actually makes the metal more brittle. So it makes it more likely to crack instead of stretch, right? So it's a double whammy. Insulate your pipes, in other words, or you're going to have, the bulk modulus is going to get you. Yeah.
Is this entered in Pascal?
No,
No, not yet.
actually, yeah, the one of the questions is, one of them asks for pressure, right? That one could be, you could either leave it in terms of newtons per square meter or pascals, I don't care. It'll take either one, right? They're the same thing. Okay, this question though, here's the part I wanted to get to. This question isn't asking that. It's asking, when the water expands, what's the force that's exerted on the end caps of the cylinder? Okay? Because a lot of times there's going to be a weak link in a system, right? Probably the weak link is going to be where the pipes are joined, right, where they're soldered together. Or for example, like if a bottle, you draw on your vast life experiences here. If you put a bottle of juice in the refrigerator and it freezes, where does this, I mean in the freezer, sorry. That's hopefully not the refrigerator, that would be bad. In the freezer, and it freezes, where does the bottle typically fail? The cap, yeah, the glass doesn't break, it fails at the cap because the cap is the weak link, right? Well, this is that kind of a question. Why is that the case? Well, let's look at the forces that are being exerted. Now, if the pressure in the water is 2.8, or the pressure being exerted in here is 2.8 times, 2 times 10 to the 8 pascals, right? Roughly, that's the pressure being exerted when the water expands. What does that mean? Yeah.
I have a question.
Yeah.
So let's say you keep like a jar of pizza sauce in the freezer because you have to save it for a later time.
Say hypothetically,
And-
yes.
and you have to heat it up and thaw it, so you put it in the microwave
Mhm.
and then you take it out and then the glass shatters. Or doesn't shatter, it just,
Cracks.
yeah.
Okay,
and then it
that's
comes up.
that's different. Yeah, I'll tell you what that is. That's something we haven't talked about yet. That's thermal stress. Thermal stress is typically going to be a bigger issue than bulk modulus. Just because it's a great question, I'm going to answer this. Do you ever notice, like when you pour concrete, has anybody ever poured concrete before?
Yeah.
Okay, when you pour concrete, can you pour one ginormous slab of concrete?
No.
You can't. If you pour one enormous slab of concrete, it will crack if the temperatures change. So what do?
Lots of small ones.
You pour small pieces and you put spaces between when you pour the concrete. If you look on a bridge, next time you have a chance to walk across a bridge,
The middle.
that's right, look at the wherever the big sections of deck connect on the bridge, usually at the spans. You can see this usually if you just look. Notice that where those meet, there's always going to be a significant gap in the bridge. How come? Because on a hot day, that's a long piece of span and it's going to thermally expand. There's going to be a thermal change in the properties of the materials, and when objects get hot, they expand. And so when the sun beats down on the concrete on the hot deck of the bridge, it's going to expand in all directions. Its volume is going to increase because there's that thermal change. And if you didn't do that, the forces are enormous. And so the two pieces would butt up against each other and they would crumble. They would just start to buckle up and crumble. You can do things like with thermal expansion, you can cut metal. You could take a hardened, how can I explain this? So if you had I gotta draw a picture. So let's say you did something like this. Let's say you have a hardened piece of steel that this is what it looks like looking on at the face of this thing. It's just this big piece of steel and there's a hole drilled in it, okay? We're going to weld this to a big plate, and then next to the plate, we're going to weld another piece that comes right up against the hole on this one, right? If I stick a piece of metal through this and I put a torch on this piece of metal, what's going to happen? What's this piece of metal? Seen from the side, it would look like this. You've got this big plate right here that's got a hole through the middle. I can put a piece of metal through that hole in the middle. And then next to that, I've got another piece of metal, and they're both welded to, say, a base plate. If I apply a blowtorch, that's my blowtorch, to this one, and heat it up,
It's going to expand up.
it's going to expand up, and it's going to shear that metal right off. And it will. The forces are enormous. So, I mean, you can't really resist this. That's why you have to build in these expansion joints when you do bridges, for example. Okay? But there's your, long story short, that's your spaghetti sauce. Spaghetti sauce?
Well,
Sort of kind of maybe.
Marinara sauce.
There you go. Okay, there you go. So what about this then? How are we going to figure this out? Now, here's something you have to visualize when you're talking about pressure. Imagine you took a balloon. What would happen if you took a thick-walled balloon, or say a basketball? If you take a basketball down deep in a pool, what's going to happen to it? You got to hold it down, sure.
It starts to it seems as though
How deep?
it loses air.
Well, say we're gonna go as deep as we need to go. It's a really deep, it's like a well. We can go as deep as we want, or it's the ocean, I
It
don't
could
care.
pop if it was really deep.
It would just crumple.
It's probably not gonna pop,
It just-
actually.
Even if you're at the
It
bottom.
looks like
It would appear to
the-
deflate.
Okay, it would appear to deflate, but here's my question. Is it going to deflate like a pancake? Is the ball gonna is it gonna flatten out this way because there's all that water weight
All
on top of it? Or is it just gonna compress inward uniformly? Compresses uniformly, it does. Compresses uniformly because pressure, and we haven't talked a lot about fluid pressure yet, that's coming up. This is kind of important to know for this problem. Fluid pressure is transmitted equally in all directions, right? Which is really crucial. That's why hydraulics work, for example, which we'll talk about soon. We got lots to talk about, don't we? So it's transferred uniformly in all directions, and so that's important. So the pressure that's acting inside of this cylinder when the water freezes, the pressure is acting equally on all the surface areas, right? So if I want to calculate, you got to think hard about this. If I want to calculate how much force is being applied to one of the end caps, how can I do that? What's the trick I could use? What do I do with my pen?
Multiply the pressure by the area.
Right, okay, so pressure is force per unit area, right? So the pressure that we calculated up here using the bulk modulus is just the fluid pressure inside the water / ice, right? Okay, if I want to know how much force is being exerted on the end cap, well, the end caps have a radius of 13.1 centimeters, so 0.131 meters, right? So all I would have to do is calculate the cross-sectional area. The area of a cap is just pi times 0.131 meters squared, right? And we know that pressure is force per unit area, right? So if I solve for F, F is just equal to fluid pressure times the area that the fluid pressure is acting on, right? See how that works?
Which is just that.
Yeah, which is just that, exactly. So we could just multiply, if I want to find the force that's acting on the end caps, the force is going to equal, what is it, 2 times 10 to the 8th pascals times that.
Would this be on the middle nubs?
What's that?
Would this be on the middle nubs?
Yes. Okay, what's that give us for an answer?
With the original,
Yeah, so
with the unrounded pressure, it's 10.7 million.
10.7 million newtons is the amount of force that's going to be incident on the end caps. Okay, would it be better if we wanted to say the caps were the vulnerable part of this? Would it be better for us to have the caps be smaller or bigger? Smaller, absolutely. So why do you think it is? I mean, probably for convenience too, but why would it be then that when we pressurize materials in bottles, that we always make the caps small? For that reason, right? Because the forces acting are going to be less, right? It wouldn't make sense to bottle a soft drink that's going to have pressure building up from the carbon dioxide coming out, and you get high pressure. It wouldn't make sense to have a great big cap on a container of that, right? You want it to be a small container so it won't be blown out by the internal pressure, right? What's that? So the units, you tell me what, we used all standard units on this, so what would the units of force be?
Newtons.
Newtons. Right, because the units of this would have been pascals, which are newtons per square meter, and the units of this would have been square meters, right, because we turned this into meters. See what I'm saying? So those would cancel, and we're left with newtons. About that.
So you don't have to do that, multiply by 6,895
No,
with the PSI?
no, that was just, that's not part of the problem. That was just I was just showing you why it is that pipes burst.
Oh,
Because the burst pressure is less than the pressure exerted by the expanding.
Can you circle the stuff that is important to the question?
Yeah, here I'll make it, okay,
yeah,
I got
where
you.
did the circle?
How about if I just say,
Well,
There you go. That's extraneous. All this other stuff was important. Okay, so and let's review real quick. So what we do? We calculated, we use this equation to calculate the amount of pressure, right, from the bulk modulus equation. F over A, which is P, just equaled bulk modulus times 0.0905, right? That gave us the pressure. And then if we want to find out the force exerted on the end cap, well, we just take advantage of the fact that pressure equals force per unit area, right? So force equals fluid pressure times the area of the cap. In fact, let me write that. That's the area of the cap. Right? So there's the fluid pressure, there's the area of the cap. Okay. How much time we got? 7. So while we're talking about this, then let's talk about hydraulics. Because we can really understand hydraulics pretty easily with this. What advantage do hydraulics have? Like if you're talking about a really big time press, you'd use a hydraulic press. If you want to squeeze metal flat, you'd use hardened steel plates, like in the movie The Terminator, right? At the end of the first Terminator, like when they squashed the Terminator, that's a hydraulic press in the first Terminator. So that's run by hydraulics. How do hydraulics work then? Whenever you look at a hydraulic machine, notice that it's always got little tubes connecting, the driving part. So like the motor of the lifter, extending along the arms of the lifter, there are these little tubes that are always bracketed to the arm. What do? Here's how it works.
Push and pull gases or water? Or
It's oil, actually. They use a hydraulic fluid that's less compressible than water. So they're going to use. So you got this big master cylinder, and you're going to press down. So this is a hollow cylinder, and you're going to push a piston down into this, right? So you've got this big piston that's being pushed down, let's say, right? Or anyway, that's connected with a little tube. That's connected to another cylinder. I got them backwards actually. This is going to be the master cylinder, which is small in radius. Okay. So we press down on this one with a plunger. It's just a cylinder, right? And we're going to press down on that, and there's fluid in here, right? So what's that going to do if I push down with a force, and this thing has, in cross section, the area is pretty small, right, of the cylinder that's pushing through the fluid, right? But I'm creating a pressure, aren't I? Right? I create a pressure. Pressure equals force per unit area. So by having a small area here, I can create high pressures. Agreed? Like if I push down with 1,000 newtons of force, and this is a pretty small surface area, I'm going to get high pressures. Well, if these two cylinders are connected, then the oil is going to flow into this, from the master cylinder into this is called the slave cylinder. It gets pushed into the slave cylinder, and the pressure is going to be the same, right? But this is a much, much larger piston, right? So the area is significantly bigger. If I look in cross section, that's the area, right? So what kinds of forces are applied then? Well, force equals pressure times area. The pressures are the same, but because the area is so much larger here, I dramatically increase the amount of force, the lifting force on that cylinder, right? And so you can magnify your force tremendously. That's just that simple. That's all it is. It's just like literally, it's like two syringes, one that's got a tiny plunger and one that's got a big plunger, and they're hooked together, and that's it, right? And when we talk about simple machines, we'll get into more detail with that. We'll talk about work and energy, and there's some pretty interesting things you can say about a hydraulic machine, but that's how it works. Okay. All right, that's a lot of physics. That's good for a day. So the last assignment's up. I'll put some reviews up, and then like practice tests, and then we'll do some tests. How about it?